Hey, welcome back, AP Calculus students. This is the final thing for our derivative stuff. Our first semester is about to end. Good job. Yeah, so we're just gonna jump into some more examples involving related rates. So just to recap, when we're dealing with related rates, we're gonna set up an appropriate equation first. Then we're gonna do our derivative with respect to time of our equation that we wrote down. We're gonna make sure that we chain rule all the necessary chain rule parts for each variable. And then we're going to fill in information. Now the first one is not so bad. It actually comes out really nicely. But the second one, there's a little bit of a trick to it. And we'll talk about it and you'll be prepared for it. So in this first problem, it says a police cruiser approaching a right angle intersection from the north is chasing a speeding car headed east. When the cruiser is 0.6 miles north of the intersection, the car is 0.8 miles east. At that point, radar detects the distance is increasing by 20 miles per hour. The cruiser is going 60 miles per hour. How fast is the car going? So calculus allows us to do a lot of neat things, and this is one of them, right? So there's a lot of things going on here. There's like speeds going on. One car is going towards the intersection. One car is going away from the intersection. There's a lot of stuff to do. And we couldn't solve this we probably couldn't solve this just using algebra and all our stuff, all the stuff that we knew previously. But once we understand calculus, then it's not that bad of a problem as long as we set it up properly. So here's our police car. Our police car is headed from the north towards the intersection, right? The intersection is here. We know that that's going to be 0.6 miles from the intersection, right? This car is moving this way, right? So that's 0.8 miles from the intersection. Now we don't know how far they are how far the distance in between them is, but we can definitely find that out. So while we're at it, let's just go ahead and find this out. If we use Pythagorean Theorem, right, a squared plus b squared equals c squared, because we do have a right angle intersection, we're allowed to do that, and a triangle. Then our a would be 0.6, our b would be 0.8, and we're trying to find our hypotenuse, the distance between the police car and the car it's chasing. So 0.6 is 3.6 plus 6.4, which is 1. Wait, I didn't do that right. 0.36 plus 0.64, which is 1. And therefore C is going to be 1. So we know that's 1. This is going to help us as we continue on with this. So notice this is a Pythagorean theorem, right? We have this. I shouldn't say x there. We have this, we have this, we have this side. So we're doing 3 sides of a right triangle. We're going to set up a Pythagorean theorem. So we're going to say that, well, let's refer back to this one. Y squared plus x squared is equal to I don't know, we'll call this c squared. It's actually probably easier if we just do like this. Let's do A, B, and C. So A represents the police car, B represents the car it's chasing, and C represents the distance between them. Okay, so let's do a squared plus b squared equals c squared, right? That's step 1. We're going to set up our equation. We know that we have 3 sides of a right triangle, so we're going to use the Pythagorean theorem. Okay, step 2, we're going to do the derivative with respect to t of this whole thing. So we have derivative of a squared is 2a, and we have to remember to do our chain, dA dt, plus we have derivative of b squared, which is 2b, and then we're going to chain dB dt, and then the last one, same thing, derivative of c squared is 2c dc dt. Okay, now let's fill in our information. So remember that A, and sometimes it's easier to do this, so it's patrol car. B is the chase car? I don't know, chase car. And then C is the distance between A and C. Okay? So what we know about the patrol car is that it's 0.6 miles from the intersection. Right? It also says that the cruiser is going at a speed of 60 miles per hour, right? The cruiser is going 60 miles per hour. So we also know the rate of change for that car, right? And because it's going towards, so this is a tricky one, right? It's because the police car is going towards the intersection here, the distance between the intersection and the car is decreasing. So our rate has got to be negative. So that's one of the key points to this one. So it's going to be negative 60 for our dA dt. Now for the car, the chase car, we know it's 0.8 miles from the intersection, right? That's our B. And then the rate of change of the car, does it say? No, it doesn't say. That's what we're trying to find, right? How fast is the car going? So we'll say dB dt there still, because we're not sure what that is. And then the last thing is we're going to do our C, right? So 2 times the distance between them we said was 1 by using Pythagorean Theorem. And it says that the distance is changing by 20, right? It's increasing by 20 miles per hour. So the distance between us, dc dt, between the two cars is going to be 20. Now let's just go ahead and clean this all up and we'll have our answer. So 2 times 0.6 times negative 60. 2 times 0.6 times negative 60 is negative 72. And then 1.6 dB dt. And then the right side is 2 times 1 times 20, which is 40. Now we're solving this for dB dt, so we're going to add our 72, which is 112. And then divide by 1.6. Is 70 miles per hour. And just checking it, right? It makes sense, right? The distance between the two cars is increasing, so the chase car has got to be going faster than the police car, which is going at 60 miles an hour, right? 60 miles an hour. So it's always good to just, at the very end, just kind of take a look at it and say, does this seem reasonable? Does this seem plausible? And then if it is, then we should be comfortable with our answer. Okay, on to the last problem, and this one's a little bit of a doozy, but once you understand how to set it up, it's not so bad. So we're looking at the water runs into a conical tank at a rate of 9 feet cubed per minute, or cubic feet per minute. So that would be the rate of the volume, right? The water is going into there, the volume is increasing. The second part of it says the tank stands point down. So if you notice our drawing, point down means that the tip is down, and has a height of 10 feet and base radius of 5 feet. So those things are labeled. Now it says how fast is the water rising when the water is 6 feet deep. So it says water rising when it's 6 feet deep. Okay, so this is kind of weird, right? So we do know how to set it up. We'll set it up first. We'll say that step 1, right, we're going to do volume for a cone. We said this last time or yesterday. It was 1/3 pi r squared h. Okay, so the thing is here, because when we do this derivative and we have 3 variables, right, it's asking us to find how fast the water is rising. So that would be, we want to find how fast the water is rising. So that's the change in height. That's the dH dt. Right, but it doesn't say anything about the radius here. right? So it doesn't say, well, it does say how big the radius is at the top, but it doesn't tell us how fast the radius is changing, which would be crucial because we already don't know what a dH/dt is. We're solving for that. But if we have another variable that we don't know, then it's going to make our life hard, and we really can't solve it if we have more than one variable to solve for. So, well, let's go ahead and do the derivative first. Let's go ahead and derive v equals 1/3 pi r squared h. All right, so we're going to do derivative with respect to t. And really, we did this last time, but I guess we'll do it again. So this is it's what's the word I'm looking for? It's a product rule, right? Because we have the r squared times h. So we have dv dt equals 1/3 pi. And then our u is r squared, so r squared dh dt, and then we have v du, which is 2r h. I should write this out. So u is r squared, du is r squared, oops, sorry, 2r dr dt, and v is h, dv is dh dt, right? So our v du 2rh dr dt. Okay, so what the problem here is that if we were to do this, we know what the radius is, we know what the height is. Those are things that we can fill in, but we don't know what the dr dt is, and we don't know what the dh dt is. So let's set this up in a little different way. So the key to setting this one up is we're gonna use this idea that we have this triangle. So we're just taking a cross section of this cone, right? We know the height is 10 and the radius is 5. What we also know about triangles is that if we take portions of a triangle, so we have a similar triangle here, and it's asking us when it's 6 feet deep, right? So that's the problem here. What we do know is that the ratio of this would be the same. So 5/10 is a half. This would be a 3/6. So the property of similar triangles is that the sides are always in the same ratio. So let's kind of set this up. So we know that the radius over the height is always going to be in the ratio of 1/2. Or you could say 5/10 or even 3/6. Right? And then what we're going to do is, because it's saying to find out how fast the water is rising, right, which we said was the change in height over time, is we want this whole thing to be in terms of h. So we're going to solve this for r. We're going to substitute for r in our equation. So let's switch to another paper. So we know that r over h equals 1/2. We said we're going to solve this for r, so we're going to multiply by h. So now r in terms of h is 1/2 h. We have our original function here. 1/3 pi r squared h. And we're going to substitute this r into r squared. So v is equal to 1/3 pi. Then we're going to do 1/2 h squared, right? That's this part, times h. And the neat thing about this is it eliminates one of the variables, right? So we only have two variables we're working with, the v and the h. We could have done the same thing. Instead of solving for r, we could have solved for h, but that wouldn't help us, right? That would tell us the rate of change of our radius, but it's asking for a rate of change for our height. So let's kind of simplify this now. 1/3 pi, 1/2 squared is 1/4, and then h squared times h. So then we have the 1/3 and 1/4 is 1/12 pi, and then h squared times h is h cubed. Now at this point, it's going to be easier to derive. We don't have to do our product rule or anything like that because we just have v's and h's. Let's change up our colors here. So dv dt equals 1/12 pi, right? Those don't need to be derived. And then we have 3h squared, and then we need to remember to chain it. So dh dt. Now that it's set up properly, we're just going to go ahead and plug in our information that we know. So we said that the volume of the tank is changing at 9 cubic feet per minute. So this is going to be 9. And we have 1/12 pi. Then we have 3 times. Remember the h here, right, is at 6 feet. So we don't want to plug in the 10. That's the total volume for the cone. But we're only looking at it when it's at 6 feet. So we're going to plug in our 6 for our h. And then we have dh dt, which is what we're trying to solve for. So let's go ahead and clean this up a little bit. So we have 1/12. 6 squared is 36 times 3 is 108 divided by 12 is 9. So 9 equals 9 pi dh dt. And then we just got to divide by 9 pi. So then we get 1/pi. Or if we calculate that, 1 divided by pi, oops, is 0.318. And that would be feet, right? Because we're measuring in cubic feet per minute. Okay, so that's it. Yeah, the conic tank stuff and the water flowing in and out of it, that's something that you probably should expect to see on your end of the year test for AP Calculus. It's something that's very common. So it's good practice. And also the trick where we convert the radius to terms of h, right, is something that we need to practice so that when we see it on our test, we're comfortable and we know exactly what we need to do. It's a little bit difficult, but the more you practice, the better you get at it. Okay, good job.